We are back for our 2020 Latin American Space Challenge conference. Today, we are having keynote speakers and also podium sessions. Like I said before, we are having a podium session now. It will be the Capital Rocket team presenting their work about the blowdown analysis for hybrid rocket motors. We have here with us Renato De Brito and Mateo Silva. Both are from the University of Brasilia. So they will have 10 minutes to talk about their theme for the podium session. So good morning, Mateus and Renato. The word is with you.
Good morning. Hello, my name is Renato, and I will present this work with Mateus. We're both aerospace engineering students at the University of Brasilia and leaders of the Capital Rocket Team's hybrid rocket project, Daedalus 2. Our presentation focuses on the blowdown analysis for hybrid rocket motors. The blowdown analysis has the objective to model the hybrid propulsion system behavior when using nitrous oxide as a self-pressurized oxidizer. The model used consists basically in four major steps: calculation of the oxidizer thermodynamic states, calculation of the oxidizer mass flow rate with a two-phase injection model, the looping algorithm for the tank emptying process, and the performance calculations. Some important points to be addressed are the correction in the injection model and obtaining the performance curves in function of the engine's operation time. To characterize the feed system behavior for a self-pressurized oxidizer as the nitrous oxide, a blowdown model is necessary in order to account for the specific behavior of this kind of two-phase propellant. At room temperature, nitrous oxide exists as a saturated fluid. This happens because the nitrous oxide has a low pressure and temperature critical points. Because it presents a compressibility factor of 0.13 for the liquid phase and 0.53 for the vapor phase, the nitrous oxide can be modeled as an incompressible liquid or an ideal gas. Also, it has a high vapor pressure at room temperature of approximately 56 bar at 300 Kelvin. For accurately modeling of the injection conditions, it is necessary to use a mass flow model that accounts for non-equilibrium and compressibility effects within the injection element during the expansion process of the oxidizer. As proposed by Deere, these considerations are made by defining a non-equilibrium parameter K that accounts for the vaporization that happens within the injection by calculating the ratio between the bubble growth time and the residence time of the fluid in the injection orifice. This parameter is used to define what regime is predominant during the injection of the oxidizer. If the bubble growth time is large compared with the liquid residence time, the flow rate should be well predicted by the classic incompressible equation. If, on the other hand, the residence time is much larger than the bubble growth time, the flow rate should approach the critical flow rate as predicted by the homogeneous equilibrium model. Then, this parameter is used to build weighting factors that define if the flow regime is more close to an incompressible behavior or a homogeneous equilibrium behavior. Although the description of Dyer is physically consistent, the original presentation of the non-homogeneous null-equilibrium equation is inconsistent. Here, in this graphic, it is possible to see that the coefficient assigned to the homogeneous equilibrium model predominates for high k values, when the opposite is physically observed. To correct this equation, Solomon proposed in his master thesis to redefine the coefficients of the non-homogeneous non-equilibrium equation as shown here. Now, the weighting factors behave according to the physical description of the flow regimes. This mass flow model is used in an engineering model that describes the oxidizer tank emptying in order to obtain the trend over time of the oxidizer thermodynamic states. This part of the blowdown model is responsible for the tank emptying modeling. For every time step of the calculation, the algorithm calculates the thermodynamic states of the oxidizer by interpolating the NIST charts that have an extensive database for thermodynamic properties for various fluids. These properties are then used to calculate the fluid quality and the oxidized mass flow rate. When this quality is equal to 1, it means that all the liquid inside the tank was expelled, and only vapor remains. The algorithm now calculates the mass flow rate of oxidizer with a compressible model, and the loop stops when the oxidized mass becomes 0. The comparison between the algorithm used for the project and the experimental results for the team propulsion system used in the Gamma 1 project were done in the work of Renato and Mauricio in order to validate the code implemented in MATLAB. It is possible to observe that pressure drop in the feed line it exists a pressure drop in the feed line, and the burning time that is considered to happen only during liquid injection. It was possible to evaluate the impacts of a proper mass flow rate model for the calculation of performance. A comparison between the incompressible model, the homogeneous equilibrium model, and the non-homogeneous equilibrium model is plotted in the image. The non-homogeneous non-equilibrium model has a better prediction of the thrust produced.
The performance calculations were done using the oxidized mass flow rate to calculate the oxidized mass flux through the grain port area, and using this calculate the regression rate of the grain for the calculation of the full mass flow rate. Having both the oxidizer and the full mass flow rate, the total propellant mass flow rate can be obtained, and with this value of the performance parameters can be obtained. Here, we present the model results of the Daedalus 2 project. The first result to analyze is the pressure drop in the oxidizer tank and how this drop reflects in the chamber pressure behavior. It can be seen that the algorithm predicts the slope of the pressure curve and the temperature curve in the tank. It's possible to see that around 5.3 seconds, the system has a sudden pressure drop. This related to the end of the liquid phase in the tank. Now only vapor phase remains. The burning time of the motor is taken to happen only during the liquid injection time, and this burning time predicted by the algorithm is very close to the burning time of 5 seconds calculated in the initial design. The pressure drop in the tank oxidizer is not
continue.
Sorry. Therefore, the mass flow rate oxidizer is not constant, so there is variation associated with the temperature, the pressure in the tank. Next, please. The developed algorithm also capable of precision the thrust curve more closely with the real behavior. The thrust curve generated by the algorithm is mainly important of the flight simulation besides the analysis of dynamic stabilization. The simulations provide the interactive work of engine design and the flight performance. For the Daedalus 2 mission, the blowdown analysis provides the average thrust of the 660 Newton with burning time of 5.3 seconds. The pressure drop in the combustion chambers is a direct consequence of the pressure drop in the oxidized tank due to the drop in the oxidizer mass flow rate during the motor operation. With these results, a more accurately prediction of the propulsion system performance can be obtained and used to improve the design process of the hybrid motor. Next. Thank you for your attention. Any questions?
Thank you, everyone, for the attention.
Thank you so much for your presentation. It was a Thank you so much. I was in the wrong output of audio, sorry. Thank you for your presentation. The hybrid rocket motors are something that I love. I think Pion team also loves hybrid motors, and I will ask if the public has any questions. Let me see. So I have just one question. It's about the. It's not just about your work with the Blowdown analysis, but with the vision that Capital and Mateus and Renato have about the hybrid rocket motors, and how you guys see the hybrid rocket motors being used a main propulsion system for small satellites launchers. For example, the High Impulse is a new startup in Europe, mainly in Germany, and they have a launch vehicle with a hybrid propulsion. Also, we have something like in Singapore. And what makes hybrid rocket motors so interesting in your vision?
Thank you for the question. I think that the use of hybrid propulsion in commercial launchers are very important because the hybrid propulsion is a type of chemical propulsion that provides knowledge of both mainly used propulsion systems, né? The solid and the liquid propulsion. And work with hybrid propulsion makes you have contact with technologies that are applicable in both these mainly propulsion types use it, and it's a very more safe than a solid system and less complex than a liquid system. So it's a type of system that can provide knowledge of propulsion in an overall way. And for applications like university research, it's a safe system. It's not very complex, not very expensive. So they extend this to commercial and commercial launches. It's a very good thing that improves the research area of hybrid rocket that is not well developed like the solid and liquid propulsion area. And I think the applications of this type of propulsion system has to be more studied and more characterized in order to have more knowledge and technology advanced in this area. So commercial use of this propulsion is very great for us that, like you said, we love hybrid propulsion.
Oh, nice answer. Thank you for your presentation, Mateus and Renato. I hope the best score for you in the Latin American Space Challenge, also in this podium session. Your work is amazing, and good luck. You guys have a future, brilliant future. Thank you so much.